going to discuss about the slope deflection problem for the frame. So this frame having three spans, that is A, B, C and then D. This is the given problem. In the step 1 we need to find out the fixed end moments. So AB is the first span we are going to consider. It carries here simply supported. It carries a concentrated load at the center. So first step we are going to find out the fixed end moments. If it having concentrated load means the formula is minus WL by 8. So this W will be capital W. So that concentrated load value W is W value is 120 kilonewton. The length of the span is 4 meter divided by 8. We are getting it is as minus 60 kilonewton meter. And then for BA span, the formula is capital WL divided by 8. Here the W value is 120 and the L value is 4 divided by 8. We are getting 60 kilonewton per meter. So next we are considering the span BC. For the span BC, we are going to calculate the fixed end moments. The formula for the UDL, it carries a UDL. So the formula for the UDL is minus WL square by 12 to find out the fixed end moment. So minus here the W value is 30 and the L value is 4 divided by 12. We are getting the fixed moment as minus 40 kilonewton meter. For CB, vice versa. So if it is minus 40 means here we will get plus 40 kilonewton per meter. Next we are going to consider the span BD. So in the span BD there is no load. Here there is no load. So the fixed end moment will be the 0. So this is the step 1. So next is step 2. In the step 2 we are going to calculate the slope deflection equations for each span. So first we will consider the span of AB. The formula is fixed end moment of AB plus 2EI by L into 2 theta A plus theta B minus 3 del by L. So we have find out fixed end moment for AB span as minus 60. So here we are substituting as minus 60 plus 2EI divided by L value. L is nothing but it is the span. So that is 4 meter and then we are having theta 2 theta A. Here theta A is 0 because it having the fixed end moments. At the fixed moment the slope will be 0. So we are substituting theta A as 0 and then theta B, and also here there is no sinking in the support. So del value also 0. Now we are getting the equation as minus 60 minus 0.551 EI. 5 EI theta B. So we will take it as equation number 1. And then we are going to find the slope deflection equation for BA. So same this formula we are getting the equation as 60 plus 2 EI by 4 into theta A plus 2 theta B minus 0. Here also the theta A value is 0 because it has fixed support. At the fixed support the slope will be 0. Only we are having theta B, and also the del value also 0 because del is nothing but it is the sinking displacement. In this problem there is no sinking displacement, so del is 0. So we are getting MPA value as 60 plus EI into theta B. We will consider this is equation number 2. So next we will calculate for the MBC, that means BC span moment. We will substitute the fixed end moment of BC span, that is minus 40 plus 2 EI by L. L is 4 meter plus 2 theta B plus theta C minus 3 del by L. Here the del value is 0. So we are omitting that portions. So we will substitute the values. We are getting the equation 0.5 EI theta B plus EI theta C. We will consider this is as third equations. So next we are going to calculate the slope deflection equation for BD stand. In this BD stand there is no fixed end moment because that stand not containing any load. So it is 0 plus 2 EI divided by L into 2 theta B plus theta D. So we are getting the final. Here the theta D is 0 because it has fixed support. So there is no slope at that D point. So we are getting the equation as EI theta B. So we will take this is as equation number 4. So next we will consider we will consider BD span. In that we are going to calculate the MdV. So here fixed end moment for dV span is 0 because no load plus 2 EI divided by L. L is 4 meter. The span is 4 meter plus theta B plus 2 theta D. Here also the theta D is 0 because it is fixed support. So remaining we are getting 0.5 EI theta B as the slope deflection equation. We will consider this equation as 5. So step 3 we need to calculate the equilibrium equations. Here we are having the joint B, that is hinged joint. So in the hinged joint we are having 3 numbers. One is BD, another one is BA, third one is BC. So moment of BA plus moment of BC plus moment of BD is equal to 0. Now we are going to substitute the values. That is equation 2 plus BC is nothing but it is equation 3 plus BD is nothing but it is equation 4. So now we are going to add these 3 equations. Finally we are getting the equation as 3 EI theta B plus 0.5 EI theta C. We will assume this equation as equation number 6. So next we are going to consider this C joint. So C joint, the summation of moment at the C joint is 0 because it has roller support. At the roller support the moment will be 0. So in C we are having only one span, that is CB, and also we are having only one moment, that is MCB is equal to 0. We are having MCB equations as 40 plus 0.5 EI theta B plus EI theta C equal to 0. Now we are going to substitute these equations and find out 0.5 EI theta B plus EI theta C equal to minus 40. So by substitutions of we will assume this equation as 7. Here we are having the values for theta B plus theta C, and also here we are having theta B and theta C. By the solving these 2 equations we can get the theta B and theta C value. So here we are getting theta B equal to 0, theta C equal to minus 40 divided by L. So now we are going to find out the final moments. So final moments, first we should find out the AB and then BA and then BC, CB, BD, DB. Totally we need to find out 6 moments. By substitutions of theta B and theta C, we are getting these final moments. So next step 4, we need to draw the bending moment diagram for the given frame. Free moment diagram for the span AB is the symmetrical, and also it has the parabola with the maximum ordinate because it carries a UDL. So for the UDL, if we are considering this as simply supported beam, what is the maximum bending moment formula? That is WL square by 8. That is WL square by 8. So we are substituting this formula. We are getting that W is 30 plus L value is 4 square divided by 8. We are getting the maximum bending moment ordinate as 60 kilonewton meter, and then span AB, we are having the concentrated load at the center. If it carries concentrated load, the maximum bending moment ordinate can be calculated using WL divided by 4 formula. So where W is 60 plus 4 into 4, we are getting 60 kilonewton, where W is 120. 120, 4 into 4, we are getting the answer as 120 kilonewton meter. So next we are going to draw the equations. So AB, BC, CB, BD, this is CB value 0. So we are mark all the values and also mark the coordinates for simply supported moment, and then we need to hatch the uncommon pattern. These portions also we need to hatch it. So this is the final bending moment diagram for the given frame section. So this diagram is more important. This is the result of this problem. Okay. The last class we have discussed about the analysis of the frame using slope deflection method, that is without sway. So in this class we are going to discuss about the analysis of the frame using slope deflection method with the sway. Okay, so when the sway will occur, if the span of that means the length of the column is varying, it has a different length, means the frame will get swayed. Okay, so this is the given frame diagram, both end having fixed supports, but the length of the AB column is 4 meter, length of the CD column is 6 meter, so it have sway. And then BC column carries a UDL load, that is 40 kilonewton per meter, and it having varying I value. If the I value varied, that time also sway will occur. Okay, so step 1, as usual, step 1 we need to find out the fixed end moments. In span AB and CD we don't have any load, external loads, so that fixed end moments are 0. So bending moment, fixed end moment at AB, fixed end moment at BA, fixed end moment at CD, fixed moment at BC, all are 0. In span BC we are having the UDL load. If it carries UDL load, means the fixed end moment formula is WL square by 12 minus or plus WL square by 12, where the W value is 40 kilonewton, L value is 6, so and then we are having 12. So in the BC step, first for the BC we are having the formula as minus WL square by 12. So we are substituting the load value and this length value, we are getting the answer as minus 120 kilonewton meter. And then we are calculating the fixed end moments for CB. So for the CB, vice versa, the sign will get varied. So minus 120 means it will become plus 120 kilonewton meter. So next is step 2. We need to write the slope deflection equation for all the 3 spans. So totally we will get 6 equations, because each span we can write 2 slope deflection equation, because if the span AB means we can write the slope deflection equation for AB and then BA, for BC and then CB, and then CD and then BC. Totally we will have 6 slope deflection equations. So first we will write the slope deflection equations for span AB. The formula for slope deflection equation is moment of fixed end moment of AB plus 2EIL into 2 theta A plus theta B minus 3 del L. Here here we know the fixed end moment of AB is 0. We need to find out theta A and then theta B. Here theta A is nothing but it is the slope at the support A. Theta B is slope at the support B. In the support A we are having fixed support. So fixed support means at that point the slope will be 0. So theta A equal to 0 and then theta B equal to 0. We need to find out only two values. One is theta B, another one is theta C. So by using these equations, we can calculate the slope deflection equation for M of AB as 0.5 EI theta B minus 0.375 del. We are substituting del because this frame having the sway. So we need to take del value and then so you keep it as this is equation number 1. So next equation 2, moment of BA. So for that moment of BA, first we will substitute the fixed and moment value, that is 0, 2 EI by L plus theta A plus 2 theta B minus 3 del by L. So in this equation, by substituting the values, we are getting this equation as EI theta B minus 3.375 del. So this is equation number 2. So next we will calculate for slope deflection equation for BC span. So the equation is bending moment of BC plus 2EI divided by L 2 theta B plus theta C minus 3 del by L. So listen, here we are going to substitute the fixed end moment of BC, that is minus 120 plus 2I value is 2I. So we need to remember that I value as 2I and L is nothing but here 6 plus 2 theta B. Theta B it carries a hinged support. So we are having the rotation here and it is also hinged support. We are having the rotation at the theta C. So we are substituting these two values also plus 3 del by L. It is the horizontal span. The sway will occur only in the column, not in the beam. So here the del value will be 0. There is no deformations or no displacement at the beam. The deformation will occur only in the column. So we will consider we are going to consider the del value for beam portion is 0. So we are substituting this del as 0. Now we are getting the answer as minus 120 plus 1.33 EI theta B plus 0.667 EI theta C. So it is equal to equation number 3. So next we are going to write the slope deflection equation for MCB. So where the fixed moment value is 120 plus 2EI, I value is 2 into I divided by L. L is nothing but that is the span 6 plus theta B plus 2 theta C minus 3 del L. Here the del value is 0. So we are substituting as 0 is equal to minus 120 plus 0.667 EI theta B plus 1.33 EI theta C. So you assume this is as equation number 4. Deflection equation for the CD span. For the CD span, the fixed end moment is 0 plus 2E. I value is 2I, that is given in the problem, divided by L. L is the span, that is 6 meter plus 2 theta C plus theta D minus 3 del by L. Here we are going to consider value because this column is deformed by the sway. So we will consider the del value. Here the theta d value is 0 because it having fixed support. So we are substituting the value. We are getting the answer as 1.33 ei theta c minus 0.33 theta I into del. So next m theta moment for the DC plus 2e I value is 2i divided by L, that is 6 plus theta c plus 2 theta d minus 3 del by L. Here the theta d value is 0 because it has fixed support. We are having only theta c and the del value, that is 0.667 ei theta c minus 0.33 ei del value. So next step 3. Step 3 is nothing but is these equilibrium conditions. So here we are having two hinged support, one at B point, another at C point. So we will consider first B point. Here we are having two span. So these two span support moment is equal to 0. That is summation of MB equal to 0. So MBA plus MBC equal to 0. So we will substitute MBA value and MBC value. We are getting one more equation. We will take it as Roman letter 1 equation. So next we will substitute the equilibrium equation at the hinged support C, that is summation of MC equal to 0. So here also we are having two strands. One is CB, another one is CD. So moment of CB plus moment of CD equal to 0. So we will substitute this value and we are getting the Roman letter 2 equations. So taking the moment on the joint, listen, this is the different part from the previous one. So here we are going to find out this sway, that is HA equal to, this is the formula to find out the sway values. HA equal to MBA plus MAB divided by L. HD equal to MCD plus MBC divided by corresponding length L. So HA plus HD is equal to 0 because if it is in the equilibrium condition, both H, when we are adding both H, it should get 0. So we will add HA and HD. We are getting the equation as 4.5 ei theta b plus 18 ei theta c minus 2.25 del equal to minus 810. And another, by using this equation, we need to find out theta b, theta c and then del values. Simplifying these equations, we are getting ei del as 23.842 and ei theta c as minus 60.127, ei theta b as 72.43. So now we need to substitute these three values in the fixed slope deflection equation and we have to find out the end moments for these 6 spans. 3 spans, 6 end moments. Okay? Analysis of continuous beam using the moment distribution method. So this is the given problem. This is a span A, B, C, D. It has varying I value 1.5, I and then 2I. So here the spans are 6 meter, 3 meter and then 8 meter. Step 1, we need to find out the fixed end moments. So this first we will consider the span AB. AB carries a concentrated load but eccentric load. So the formula is minus WAB square divided by L square. Now we are substituting the value for W. W is nothing but 60 kilonewton and A is 4 meter, B is 2 meter. So L is 6. So we are substituting the value and we are getting answer as minus 26.67 kilonewton meter. Like this, we are calculating the fixed end moments for BA. The W is 20, L is 3, W L square by 12. Has simply supported beam only, it is 8. If it is fixed beam means the fixed end moment is 12. So minus W is 20 into L square 3 square divided by 12. We are getting the answer as minus 15 kilonewton meter. And then CB, it is 5 plus 15 kilonewton meter. So next we will consider the span CD. For the CD we are having concentrated load at the mid span. So for the mid span we are having the equation as minus W L by 8. So W value is minus 30, L is 8 and then divided by 8. We are getting minus 30 kilonewton meter. So next for CD, for DC we are getting 30 kilonewton meter. So now we need to find out the rotation factor. Rotation factor formula is nothing but it is minus 1 by 2 K divided by summation of K. K is nothing but it is the stiffness of that particular span and then summation of K is the overall stiffness values. So now step 2, we will calculate the stiffness factor for individual span. So we will consider the joint. So joints are B and C. Members are BA, BC, CB, CD. So we know if the far end is hinged means we will have the equation as